So let's take a look at some elementary number theory. We're going to look at a few different problems, see some examples of how to tackle some things, and in a couple of cases, what not to do. So the first type of proof that we typically see is a direct proof. So we're going to apply a direct proof to a straightforward claim. We will let n be an integer. If n is even, then n squared is even. So in a direct proof, we start with the hypothesis. The hypothesis in this case is that n is an even integer, and we apply definitions or other known facts to eventually conclude something about the conclusion, that n squared is even in this case. So starting with the hypothesis, we suppose that n is an even integer. By definition, that means that there exists some integer k so that n is equal to 2 times k. Then we square n. So n squared then is the quantity 2k squared, which is equal to 4 times k squared, and we can factor out the 2. So 2 times the quantity 2k squared. At this point, we have n squared is equal to 2 times something. Since that something is itself an integer, and this follows from the closure of multiplication, 2 times k squared is an integer, n squared is 2 times that, and so therefore n squared is even. And so we started with our hypothesis, reached our conclusion, and so our proof is concluded. We could do the same kind of thing, a direct proof, with a modified claim that if n is odd, then n squared is odd. Again, assuming that n is an integer. So we start the same kind of way. Suppose that n is an odd integer. We don't specify which odd integer, just an odd integer. In this case, from the definition of odd, it means that there exists some integer k so that n is equal to 2 times k plus 1. So this mimics what we just did, only now we have an odd integer rather than an even. Now when we square n, we get n squared is equal to 2k plus 1 quantity squared, expanding that, and we have 4k squared plus 4k plus 1, which we can then, again, group the first two numbers together, 4k squared plus 4k, and factor out a 2. So we have 2 times this quantity plus 1. The quantity is an integer, and so 2 times an integer plus 1 fits the definition of being an odd number. So n was odd, n squared is odd, and we have reached our conclusion. Let's look at a modified claim then. In this case, we're claiming that if n squared is even, then n is even. So if we try a direct proof in this case, we suppose that n squared is an even integer, just as we've done in the previous two examples. This means that there exists some integer k, so that n squared is equal to 2 times k. Remember, our goal is to get to some statement about n being even. But n squared is equal to 2 times k. The only way that we can see to get to n is to take a square root, and then we have square root of the quantity 2k, and we don't have anything to work with. We don't know where to go in that case. So at this point, trying a direct proof, we have no way to get to the statement n is even if we began with n squared being even. So it takes us in a wrong direction, and so instead of attempting a direct proof, we need to try something else. So instead, we have a different equivalent method, a proof by contrapositive. So in this case, our claim was that if n squared is even, then n is even. And instead, we can write the contrapositive of that. The contrapositive of the statement is the negation of the conclusion. So rather than n being even, we assume that n is odd, and then the conclusion is the negation of the original hypothesis. So the contrapositive of the claim is if n is odd, then n squared is odd. And the conclusion that we have from logic is that a statement and its contrapositive, so a conditional statement, if P then Q, and its contrapositive, if not Q then not P, are equivalent. So if one of them is true, the other one is true. If one of them is false, the other one is false. And so if we can prove the contrapositive, then we have proved the claim, not in a direct way, but kind of going at it from a different angle, a different perspective. And so the claim, if n squared is even, then n is even, was difficult for us to see what to do with a direct proof. But the contrapositive, we already know something about the contrapositive. We've already proved the contrapositive. So what that means is we've already proved the statement, if n squared is even, then n is even, when we proved the statement about odd integers. And so we can improve our claim since we proved that if n is even, then n squared is even, and now we know if n squared is even, then n is even. So what we actually have is this series of statements has proved that n is even if and only if n squared is even. And so again, there's the two parts of that. It says if n squared is even, then n is even. And if n is even, then n squared is even. So there are two parts in this if and only if statement. And we had to prove both parts separately, and we did those in different ways. One part, if n is even, then n squared is even, we proved with a direct proof. The other part, if n squared is even, then n is even, we proved by proving the contrapositive. So we know something about even integers. What does it mean about an odd integer? Well, again, we have an improved claim in that case, which we need to finish the details. But if we replace the word even with odd, then the improved claim holds for odd numbers as well. So an integer is odd if and only if n squared is odd. We've seen some examples of problems where we need to prove these by induction, and a proof by induction involves two parts. First, we show that the claim that we're trying to prove is true for at least one integer in the given set that we're talking about. So again, we're talking about a set of integers. Usually we're talking maybe about all positive integers or all integers bigger than a particular number. And so we have to show that the claim is true for at least one of these. In particular, we show it's true for the smallest one of the numbers that we care about. So if we're proving something's true for all positive integers, we start with n equals 1. If we were proving something is true for every integer bigger than 20, then we start with the first integer that's bigger than 20. So n equals 21 would be our starting point. If we had negative numbers, maybe something was true for negative numbers that are negative 10 and larger, then we would again start with negative 10. All right, so we show that it's true for at least that one integer, the smallest one that we care about. And then we show that if the claim that we care about is true for one number, then it's also true for the next number in the set. And so if we're proving something for even numbers, let's say, then the smallest one, say positive even numbers, the smallest one is 2. And then we have to show that this claim works for the next number. So that would be the next value from any even number. So if you had an even number k, the next one would be k plus 2. But usually, if we're looking at just all integers, we prove something is true for, say, 1, and then we assume that it's true for a value k, and show that it's true for the value k plus 1. So notice that this is an if it's true for one number, then it's true for the next number. And in induction, you have built into it a direct proof, usually. And so if you satisfy these two parts, show that it works for one number and then show that it always works for whichever number you found, it works for the next one as well, then basically we've lined up dominoes and knocked over the first one, and so they all fall down. And so it follows that the claim is true for all the larger values in the set. It was true for the first one. We showed that. This second one then follows from the second part of the statement here. And so since the second number is true for the second number, then it's true for the third number, so then it's true for the fourth and true for the fifth. And so by proving something with induction, basically what we're doing is proving infinitely many things, but we do it in a general way. And so it is a claim, we prove a claim for all integers in a certain set, and we can do it in a very efficient manner. And so a claim that we've seen is that if you add up all the positive integers from 1 up to a particular place, so 1 plus, we write this as 1 plus 2 plus the dots up to n. If you stopped at 1, then the plus 2 is actually, there's a little bit of technicality there. So you don't list anything bigger than the number you care about. So if you were stopping at 1, there wouldn't be anything afterwards. If you were stopping at 2, again, there's nothing afterward. So whichever number you stop at. The sum of this is achieved by taking that last value, multiplying it by the next number, and then dividing the whole thing by 2. And so a proof by induction of this would start by showing that the claim is true for the integer 1, because that's the smallest positive integer. This is the base case. And since 1 is equal to 1 times the quantity 1 plus 1, all divided by 2, the claim is true in that case. And so now what we need to do is we need to prove that if it's true for one number, then it's true for the next number as well. And so this is actually a direct proof here of this statement. If it's true for one number, then it's true for the next. So we suppose the hypothesis. We assume that the hypothesis of that claim is true, that it is true for some integer k that's greater than or equal to 1. This isn't a huge stretch because in the worst case, k is just equal to 1. K equals 1, we already showed that this works. So we're not making a huge leap here. This claim is acceptable. We're not assuming something is true for some without reason, right? We have reason. K equal to 1, we know the formula works. And so then what we're going to show is that it will work for the next number as well. And so we start by adding up to k and then adding on k plus 1. So we're adding from 1 all the way up to k plus 1. Again, notice that the 1 plus up to k, the formula works, so we replace that part with k times k plus 1 all over 2, and then adding on k plus 1. So that part is from our assumption. What we're trying to get to then is that if you add it all the way to k plus 1, on the right-hand side, what we want is k plus 1 times k plus 1 plus 1 all over 2. So we're looking for k plus 1 times k plus 2 over 2 to come out of the right-hand side. All right, so we have this quantity on the first part, and then we have this quantity. So to combine these, we need common denominators. Common denominator of 2, and we combine the terms and end up with exactly what we were looking for. K plus 1 times K plus 2 over 2. In this case, we combine these over the common denominator of 2 and then factor out the K plus 1. And when you factor out the K plus 1, we're left with K plus 2. And so we have the format we're looking for. And since this is what we were trying to prove, we have proved that if n is any positive integer, then the sum of the numbers from 1 up to that positive integer is given by n times n plus 1 all over 2. So we started with a base case, proved an inductive claim, so started with an inductive hypothesis that we assume, and prove the formula works for the next value. And so we achieved our goal, and we have proved the claim. We could prove that same thing with a direct proof and not use induction at all. So for using a direct proof in this case, let's let n be a positive integer, and then just define the sum of 1 up to n by this value s sub n. We don't know what the sum is because we don't know what n is, but as soon as we know n, we could calculate and find out the corresponding s sub n. Addition is commutative, so you can turn the order of things around, and so s sub n is also equal to, if we started at n and added our way down to 1. So we have the same value that we could calculate in two different ways. We could count up to n and add as we go, or we could count down from n, count down to 1, and add as we go. And so just kind of filling in some of the pieces here, we have 1 plus 2 plus all the way up to plus n minus 1 plus n. In the reverse order, we have n plus n minus 1, counting our way down, plus 2 plus 1 at the end. If we add these together, on the left-hand side, we get 2 times s. On the right-hand side, looking at each portion separated by plus signs, we have n plus 1 right here. Then here we have n minus 1 plus 2, which is also n plus 1. Work your way down through each one of these things, and we can see that each portion adds up to be n plus 1. How many of these n plus 1s are there? Well, there's one n plus 1 for each of the numbers. We went from 1 to n. So there are n plus 1s. So at this point, by adding these together, we have 2 times s sub n is equal to n times n plus 1. Well, we don't want 2 times s sub n. We want to know what s sub n is. So what do? Divide both sides by 2, and that gives us that s sub n, the sum of the numbers from 1 to n, is n times n plus 1 over 2. And so that's what we were looking for. And so in this case, we've proved this statement directly rather than using a proof by induction. And there are lots of other ways to prove this same statement. There's some nice proof by picture, although we have to be really, really careful of proving something with a picture, because pictures can be misleading. All right, so what would happen if instead of adding the numbers 1 plus 2 up to n, if we added the cubes of those, 1 cubed plus 2 cubed all the way up to n cubed? So this time we're not given a formula, we're just told to find and prove a formula. And so the first step is we have to find a formula. And so to find a formula, usually we want to look at some examples. And in looking at these examples, hopefully we can find a pattern. And if we can find a pattern and then prove that pattern, then we have found a formula that works. Now, a lot of times we will think we have found a pattern in data, and there's not really a pattern there, or we haven't found the correct pattern. And we realize that a pattern is incorrect if we continue on a little bit further and it breaks. It doesn't continue in the way that we had anticipated. But if we look at this starting just term by term, 1 cubed is 1, okay. 1 cubed plus 2 cubed is 9. 1 cubed plus 2 cubed plus 3 cubed is 36. And we're looking at these values, 1, 9, 36. These are numbers that we've seen before. They look familiar. And so maybe we start to see a pattern here. 1 is the same thing as 1 squared, which, again, there's nothing maybe important in that, but we just notice it. If we look at 9, 9 is the same as 1 plus 2 quantity squared. So what do you think about 36? If you look at 36, 36 is 1 plus 2 plus 3 quantity squared. And so it looks like we might be onto something here. 1 cubed plus 2 cubed plus 3 cubed is 1 plus 2 plus 3 quantity squared. If this continues, go to the 4 cubed, go to the 5 cubed, and so on. If this pattern continues, then we have a formula. And what we want to do now is, first of all, state that. The claim, our guess right now, actually, is that the sum of cubes is the square of the sums themselves. And so adding up the values 1 cubed plus 2 cubed all the way up to n cubed, based on 3 examples which may or may not be accurate, and may or may not carry on, we are guessing that that value is 1 plus 2 plus all the way up to n, and then square that answer. And so how would we go about proving this? Well, to prove a claim like this, again, it seems reasonable to consider a proof by induction, where we start with the base case. We already proved the base case, 1 cubed is equal to 1 squared. And we actually showed a couple of other cases as well, so we've kind of gone a little bit further. But now we would assume that this works for some k that's bigger, greater than or equal to 1, and then show that it works for the next value as well, so that this formula works. If we modify that a little bit, we went from just the numbers themselves to cubing them. What if we squared instead? So 1 squared plus 2 squared up to n squared. And so the same kind of approach, that we want to look at some data, see if we can find a pattern. If we can find a pattern that seems to work, then we apply this pattern to some examples, make sure that it's working, and then try to prove that that pattern works. Again, in this case, probably a proof by induction, although, again, there are other ways to do this. Now, we would possibly think that squaring something is easier than cubing, but it turns out that this pattern is a little bit harder to find. If you've never seen this before, I strongly encourage you to try to find a pattern based on the data. Don't look things up. Looking things up defeats the purpose. See if you can find a pattern by looking at some data. If you can't find a pattern by looking at some data, there are some other mathematical techniques, some tricks you can do, or you can eventually, if you must, look up a formula, but don't look up a proof of the formula. Try to prove the formula yourself. Okay, so now let's look at something that's maybe a bit more complicated example. Here the claim is every integer is either even or odd, but not both. We had looked at earlier, we kind of assumed this statement earlier when we separated things into even and odd numbers. But every integer is either even or odd, but not both. What this claim actually has in it there's several pieces. First of all, we have to prove that every integer is one of those two, even or odd. And then we have to prove that you can't have a number that is both of those. And so let's start with an integer, right? Again, not specifying the integer, but just the fact that it is an integer. And then what we need to do is, by definition of even and odd, that means that we must show that either n is equal to 2 times q or n is equal to 2 times q plus 1 for some integer q. And so you have the number n. We first of all have to show that we have either 2 times q or 2 times q plus 1. Again, not specifying the n or the q, but we must show that such a number exists. And then for the but not both part, we have to show that there are not two distinct numbers, say s and t, two distinct integers, so that n is equal to 2 times s and n is equal to 2 times t plus 1. So there's nothing about the definition that would preclude such an occurrence. There's nothing that would make it obvious that you can't have 2 times s and 2 times t plus 1 equaling the same particular number. So how do we go about proving this? Well, to go about proving this, it's not from first definitions. What we need here is the division algorithm. And the division algorithm tells us that division, rather than writing it as n divided by something, we write, again, in number theory, we focus on the multiplication and addition. So we would write that as, to divide by 2, what we have is we would write n equals 2 times q plus r. And the division algorithm tells us that these numbers are unique, the q and the r are unique, and that r is 0 or 1 in the case of looking at division by 2. So it tells us that every integer can be written as either 2 times q or 2 times q plus 1, and it is unique for that. And so the division algorithm, or the proof of the division algorithm, proves that every integer is either even or odd, but not both. So the division algorithm actually proves more than that. It goes beyond just this case. But this claim turns out to be a corollary, a subset of the claims that are made in the division algorithm. And so the idea is that this is a bit more complicated. It's not just using definitions. It's those definitions are used to prove the division algorithm. So that theorem is then used to draw other conclusions. It's still elementary in the sense of what elementary number theory means. It's still developed from first principles, so it's developed from the definitions, but there are a couple of stages in between. The other types of number theory, say analytical number theory, involve using, say, complex analysis, or there's algebraic number theory, which uses other advanced algebra techniques and so on. So it's still what we call elementary number theory, but it's not directly just from definitions. We've built some tools before we get there. And again, that's how all of mathematics builds, right? We learn something, create some new theorems, and use those theorems to prove other things, and then use those to prove other things, and so on. And so we built up this this bigger and bigger toolbox. Now, if we did not specify that s and t are integers, then it turns out that we can find distinct numbers s and t, so that n is equal to 2 times s and the same n is also equal to 2 times t plus 1. And so, for example, if we let n equals 4, then s is 2, and t could be 3/2. Okay, so if we don't specify integers, then although it feels like, oh, you can't have 2 times s and 2 times t plus 1 being the same number, you can if you allow fractions. If n was not an even number, if n were an odd number, say 5, then s would be 5/2 and t would just be 2. And so you can see something there. If you have an integer that's even, then the s value in this case would be an integer as well, and the t would be a fraction. If the number is odd, then that's reversed. So it is important in the proof idea that we specify that we're looking at integers and not just any number. So we've looked at direct proofs and some indirect methods, the contrapositive, proofs by induction, and then some more complicated things where we still maybe do a direct proof, but it doesn't look like a direct proof because of the statement isn't in the form if something, then something else. But let's take a look at another claim. If n is an integer, then n squared minus n is always even. Now we can try this examples. You can try some examples and check to see if it seems to be true. And the examples you try will give us confidence. Yeah, okay, the claim is probably true. But remember that no number of examples are enough to prove something is always true. We have to have a proof. A single counterexample can disprove, but no number of examples can prove something. All right, so for the proof idea, we could proceed by induction if we focused only on, say, positive integers. But this claim is for all integers. But if we did temporarily focus on just positive integers, then the base case would be n equals 1. And we would start off by checking to see whether 1 squared minus 1 is an even number. And so the question is 0 even? And 0 is divisible by 2, so yes, 0 is even, and the base case would work in that setting. Again, the problem here is that induction has to have a smallest starting point, and in this case, we've said let n be any integer, and so there is no starting point. There is no smallest integer. So instead, we could try a direct proof, or a more direct proof, and considering what happens with n squared minus n. So we want to show that n squared minus n is even. So we look at n squared minus n and remember that it's equal to n times the quantity n minus 1. And so we can separate this then into two cases. Now that we know and have determined from the previous example, the previous claim, that every integer is either even or odd, but not both, we have two cases. N squared minus n, which is equal to n times n minus 1, we can separate the n value into one of two cases. We can have case 1 where the integer n is even, and when we look at the integer n being even, what do we have? We have n squared minus n is equal to an even number times something else. Even number has a factor of 2, which means n squared minus n has a factor of 2. So if n is even, then n squared minus n is even. Case 2 is the integer n is odd, and when we look at that, n is odd. What does that mean about n minus 1? If n is odd, then the number before it was even. We have to prove that, but if n is odd, then the number before it is even. And so what happens, n squared minus n, is again equal to an even number times an odd number. And so breaking this into cases, rather than focusing on all of the numbers, separating it allows us to more easily solve the problem, prove the theorem in this case, or prove the claim. We've looked at this idea of a prove or disprove and salvage if possible. And so if we have a claim, say, let n be an integer, then 6 times n is divisible by 4. And so if it's a prove or disprove, we have to check to see whether the claim is true. And again, remember, to disprove a claim, we only need a single counterexample. So we can find lots and lots and lots of integers so that 6n is divisible by 4, but just one counterexample is enough to disprove the claim. And if we let n equal 1, then 6 times 1 is 6, and 6 is not divisible by 4. Remember again that is divisible by has the very specific meaning that 6, if it were divisible by 4, would be 6 equals 4 times some k, where k is an integer. We're not just saying, can you divide it and get, say, a fraction, or can you get some kind of other value. It's very specific meaning in this case. Okay, so n equals 1 is a counterexample, which means the claim is false. So we have disproved the claim. So once we've disproved the claim, now we want to try to salvage it. We want to try to figure out when it is true. And if you've experimented with this, if you've experimented with this, then you see some values that will make 6 times n be divisible by 4. If you haven't, take some time and look for some pattern to the things that make 6 times n be divisible by 4. So a salvaged claim, then, we notice that if n is even, then 6 times n is divisible by 4. And we can kind of get the idea of that to be divisible by 4, we have to have two 2's, right? 2 factors of 2. And 6 has one of the factors of 2 that we need, and then n would have to have the other one, and the only way for there to be another 2 in there is if n is even. So we still need to prove the salvage claim, but that's a salvage of the claim. But we can do better than that. We can have a more improved salvage that says if n is even, then 6n is divisible not just by 4, but by 12. And so, again, this works with any even number, whether it's positive or negative or 0. And so what happens in this case, the salvage modified the let n be an integer to let n be an even integer, and then it improved the conclusion that not only is 6n divisible by 4, it's divisible by 12. Again, divisible by 12, something divisible by 12 is also divisible by 4, but this gives us a stronger conclusion. So we modify the hypothesis and get a stronger conclusion. And again, where does the 12 come from? Well, n is even, so there's a 2 in n, and there's a 2 in the 6, and then there's a 3 in the 6. And so 2 times 2 times 3, these factors are all there, and that gives us a number that's divisible by 12. So the prove or disprove and salvage if possible idea is a bit more difficult than other scenarios because you don't know whether the thing you're looking at is true or not. And in real mathematics, when you're doing like research, you don't know. You come up with an idea, you have a conjecture based on some data, some evidence, but you don't know whether it's true or not. So you try to prove it. If that doesn't work, you spend some time trying to disprove it. You go back and forth. Sometimes trying to disprove something will trigger an idea that allows you to figure out how to prove the thing. Sometimes trying to prove something creates a scenario of a counterexample, allows you to disprove the statement. But once you've proved or disproved something, then the idea is to try to still make it better. So if you've proved it, you try to improve on that. If you've disproved it, you try to fix it a little bit, tweak it to make it something that is true, and then prove that thing. And so this idea of prove or disprove and salvage is really useful in all forms of problem solving. So, as usual, if you have any questions, feel free to ask in the comments, send an email, or find me on Discord.